Hey, this is Math 6, Unit 1, Lesson 15, called More Nets, More Surface Area. So we're going to continue our discussion today about nets. That's talking about things that wrap around three-dimensional shapes, and talking about surface area. That is the area that covers those three-dimensional shapes. So first of all, we start here with this little cube here, rectangular prism. And it says, what do you notice? What do you wonder? And it's called wrapping paper. It says, Kieran is wrapping this box of sports cards as a present for a friend. What do you notice and what do you wonder? So take a few moments with your partner there and talk about what do you see happening with this rectangular prism with the information that is provided there. A few things you might notice there, if you've already paused and come back in, is that we only have, first of all, two measurements. We have a length here and a length there. I can't tell for certain if this length is the same or not, but for now let's assume it's not and just say I don't know what that third length is going to be. It almost looks like a square, but I don't know for certain, so I'm not sure. I do know that if I multiply this length and that length, I end up with a value of 10, which tells me that the bottom area of this rectangular prism, and the top area of the rectangular prism has a value of 10 10 square units, 10 square units there, based upon what we see, because 4 times 4.25 is 10. I don't know what these are going to be. What else do we notice there? Well, we know that it is a rectangular prism. Okay, so we notice that. We notice that we have two lengths. We notice we're missing one. So just some things you might notice there. We don't know if you're wrapping that up, how many cards fit in the box. We don't know how big the cards are. We don't know a lot of things, but just things you might wonder or think about. Okay. In the next activity, though, moving on to more what today was about, is called Building Prisms and Pyramids. Your teacher will give you a drawing of a polyhedron. You will draw its net and calculate its surface area. And so today in class, your teacher probably gave you one of these shapes here. And so we have, first of all, we have shape A, which is a rectangular prism, B, which is a triangular prism, C, which is another prism here itself, and then we have a triangular prism D, and E, we have some pyramids in F and G. We have this trapezoid shape with also a triangular on the end, so to end up, not trapezoid, but a quadrilateral shape. We have a square, a rectangular thing, followed by a triangle, make this funky shape. And then we have this one, which is like a cube with a pyramid on top. So the idea here is we're going to pick a shape, and I'm going to go ahead and use shape B for the shape we're going to talk about right here. Okay, so for shape B, what it wants us to talk about then is, how are we doing this here? Where did we go? That's strange. There it is. Huh, it like disappeared. Sorry about that. That was weird. The camera just showed black, even though the picture was there. So with our first shape, I'm going to just draw a quick little sketch of it. So I have a picture to look at. It looks like this. It goes across this way, and that way. And we know we have that triangle on the back side, and the back lines connect there. And we have a height of 8, a base here of 6 on that side. We have this length of 15, and this cross section right there is 10. So what polyhedron do we have right here? Well, it has a triangle for the bases there. So this would be a triangular prism. This is dealing with B is the one I'm using here. Your teacher could have given you any one of the other ones. I'm just choosing B to give as an example here. It says to study your polyhedron, then draw its net on graph paper and use the side lengths of a grid square as the unit. So if you had some graph paper, which I don't have anyway today, I'm at my home today, so I don't have that. I know that what I have a couple things. I know I have that triangle that has a height of 8, a length of 6, and the diagonal there, or hypotenuse, of 10. We know we also have a length of 15, which is going to be carried around all the way around. Okay, so a couple things we know. We know that I'm going to have a length every time of 15 for, when I draw this net. So I can draw a length of 15. I'm just going to just draw 15 here. Maybe I want to use, let's do this. I'll use a, I'll back up a little bit since I don't have graph paper. Let me make a little sketch here. Ooh, 15, that's huge. That's a terrible idea. I was going to use a ruler, but I don't have a space. Sorry. So we're just going to just eyeball it out here. So if I went down about 15 like this, my 15 becomes my length for, let's say for example, this space or this face right there. But this face has a length of 15, but it also has this width of 10. So I would come across here, something like there at about 10. And so that face is a 15 by 10 face. That's this front one right there. The one on the back side of the triangular prism, it has a length of 10. Oh, sorry, it has another length of 15 because they're all 15 across, but it has a length here of 8. So I'd come across here and make that about an 8, like so. And then this bottom piece right there has again that length of 15, and it has this width here of 6. Alright, so that's what we're looking at so far. Now for the triangles were a little trickier to draw, or they can be at least. I had to think a little bit about where I want to put that triangle. I can't put it anywhere because I have to have a triangle that has a base of 6 and then an 8 and then a 10. And so it needs to somewhat pretty much it needs to actually go in that order. The right angle goes between the 6 and the 8. So between the 6 and the 8 here, I'm going to put a line right there. Because why? Because this part, 8, has to line, when it folds up, has to match that shape right there. And I'm going to make the diagonal part here the 10, which makes the most sense because this is going to be a longer line than that one. And then I'll do a second one over here with a 6 and an 8 and a 10. Alright, so that becomes the net for the shape that I was talking about, my triangular prism, something along those lines. You're going to draw your own that matches what you have there, but that's what I would draw for number 2. That's my net. It says to number 3, label each polygon on the net with a name or a number. Alright, so we come back over here, and we can call this part A, part B, part C, part D, and part E. Okay. And then find the surface area of your polyhedron and show your thinking in an organized manner so it can be followed by others. Alright, so let's look at the surface area. If I'm looking at the surface area of part A would be the length times the width, or 15 times 10, which is 150. If I'm doing the surface area, the area B, that would be 15 times 8, 15 times 8, which in our case here equals 120. For part C, it's 15 times 6, 15 times 6, which equals 90. And then I'm left with part D, which is a triangle, which will be 1/2 of the base, 1/2 of this base times the height. Right? So this becomes half of 6 is 3, 3 times 8 is 24. And E is the exact same. It's also 1/2 times the base times the height, which is 24. So our surface area will be all of these areas combined, giving me a total of 408. That's the surface area for that shape right there, 408. So when finished, pause for additional instructions from your teacher, but we are finished, so we're good right there. Alright, so your third activity was about comparing boxes. Back in here a little bit. It says, here are the nets of 3 cardboard boxes that are all rectangular prisms. The boxes will be packed with 1 centimeter cube. So we're going to fill them up in a little bit here, and all the lengths are in centimeters. The first question says to compare the surface areas of the boxes. Which box will use the least cardboard? So we're talking about which box will use the least cardboard because that's going to be the surface area. Alright, so to do that, what I want to find is I want to find the area of each section of each box. So that's found by multiplying the length and the width. So 3 times 3 here is 9. 3 times 2 for this box is going to be 6. 3 times 2 is 6. 3 times 2 is 6. 3 times 3 is 9. And 3 times 2 is 6. So for box A, I have a 9 plus 9 plus 6 plus 6 plus 6 plus 6. And when you add all those up, you end up with 42. Over here, I have 6 times 3 is 18. 6 times 1 is 6. 6 times 3 is 18. 6 times 1 is 6. 3 times 1 is 3. And 3 times 1 is 3. So the surface area of this box would be 18 plus 18 plus a 6 and a 6 and a 3 and a 3. And when I add that up, I end up with a surface area of 54. And finally over here, 3 times 3 is 9. This is all squares, so these are all 9s all the way around. And there happen to be 6 of them. 1, 2, 3, 4, 5, 6. 9 times 6 is 54. So the box that would have the use the least cardboard because it has the smallest surface area, okay, the least cardboard would be box A. And that's because it has a value of 42 this is centimeters, so we would say square centimeters in this case here because it said they were centimeters cubed would fit inside of it. So all the lengths are in centimeters. So 42 square centimeters is the smallest one, so it would use the least amount of cardboard there. Okay, so we've been talking about surface area for quite a while. The other thing this question mentions is it talks about packing that box with 1 centimeter cubes. So this problem involves two things. It involves surface area, and as we'll see in a second, we're also going to just talk a little bit about volume in this problem as well. So the surface area is what we've been finding for the last few lessons by multiplying lengths and widths and finding out what that space shaded area is for that, what covers the surface there. Okay. When we talk about volume, we're not talking about what covers the outside, we're talking about what fills the space inside of an object. So when I have that cube, we're talking about how much space is inside of that object. Okay, it's the number of cubes, that fit inside a box. And that's what we're dealing when we're talking about volume here. And generally, when we talk about volume, when we multiply the side lengths of a rectangular prism, that will give us the volume for how many cubes would fit inside of there. So for each of these shapes, we can find out a volume, which is what the next question asks you to do. It wants us to find a volume for each one of these shapes. It says, now compare the volumes of these boxes in cubic centimeters. Which box will hold the most? All right. So when I come back over here and I look at box A, all right, box A has several side lengths here. It has a side length of 3. It has another side length here of 3. This one matches, so I don't have to worry about it. That goes to there, so I don't have to worry about it. But the additional side length is right here, which is a 2. So for our volume for A, our volume is going to be equal to 3 times 3 times 2. 3 times 3 is 9, and 9 times 2 is 18. So we would say actually the volume is 18 centimeters cubed. It's cubic centimeters when we talk about volume because that's how many 1 centimeter cubes fit inside of there. When I look at B, the volume here, we're going to look at its sides. We have a side length of 6 and 3 and 1. So the volume is 6 times 3 times 1. 6 times 3 is 18 times 1 is 18. So 18 centimeters cubed. So these two shapes actually have the same volume. Let's take a look at the last one here. We have 3 times 3 and then times 3. So the volume of this is 3 times 3 times 3. 3 times 3 is 9, times 3 is 27 centimeters cubed. So the box that has the greatest volume is going to be box C because it can hold 27 little centimeter cubes inside of it, where the rest can only hold 18. Alright, so that's a little bit about volume as well, and surface area, and how those two things connect together with our nets today. So we're using nets to find out surface area and then folding together in order to find out what a volume is going to be. Let's take a look at your summary of today's lesson. And yes, I'm skipping the are you ready for more for today. Okay? Alright. The surface area of a polyhedron is a sum of all the areas of all the faces. So surface area is a sum of all the area of all the faces. So when I take this square pyramid here, we have all these faces here, and I have, if I fold it apart into a net, I can see I have the 6 by 6, and I have these triangles that have a base of 6 and a height of 5. And if I combine all together, it will give me a surface area. And in this case here, with this example, we end up with a square pyramid with a surface area of 96 units right there. We're going to pause there, give you a moment to do your homework, and then we'll come back and check it in just a second. Alright, here we go. Homework for lesson 15. It says Jada drew a net for a polyhedron and calculated its surface area. What polyhedron can be assembled from this net? So we can see that we have several rectangles here, which tells me most likely we're dealing with a prism, and we have a couple triangles. Because the triangles seem to match, I'm going to go with that this is a triangular prism. Okay? Because triangles are going to be parallel to each side, become my bases, and the rectangles go around that. Now it says Jada made some mistakes in her area calculations. What were the mistakes? Okay, let's take a look. So the area is found by multiplying the base times the height. 4 times 5 is 20. That looks okay. Here this 4 carries over here, so we have a length of 4. And so 4 times 4 is 16. That looks okay. Here 4 times 3 is 12. That looks okay. So now we're talking about the triangles here. And we have, for a triangle, it's 1/2 of the base, which is 3, times the height, which is right there. Those go together. Be careful there. And that's 4. So half of 3 times 4 is going to be equal to 6. Oops, she said 12. And she said 12. So the correct area for these spaces right here would actually be 6, wouldn't it? Alright, so her mistake was in the triangle part, finding that she found the wrong area there. She probably forgot to cut it in half. So the actual surface area would be a combination of the 20 plus the 16 plus the 12 plus one triangle plus another triangle. When you add all those up, we end up with 60 square centimeters. Number 2. A cereal box is 8 inches by 2 inches by 12 inches. So let's go with a 12 on this side. Let's go with an 8 on this side. Let's draw that like that. And then let's put a top on it like this. Alright. And then we're going to make this length right here of 2. Okay, so that's our cereal box there. Looks great. What is the surface area? Show your reasoning. And if you get stuck, consider drawing a sketch. Well, you already drew a sketch. I like to draw sketches when I can. It just helps me visually see what I'm talking about. So for this cereal box, we're going to have this 12 by 8 side. 12 by 8 side. And so 12 by 8 is actually 96. And I have 2 of those, right? The front and the back. 96 times 2 is 192. I'm also going to have this 12 by 2 side. So 12 times 2 is 24, and I have it on the front and the back. So times 2 becomes 48. And then I have this 8 times 2 side, which is 8 times 2 is 16. And again, I have 2 of those for the top and the bottom. So that's going to be 32. And the surface area will be combining all of those together. So when I combine all of those together, we end up with 272 square inches. And square inches because why? Every one of the units was an inch right there. Alright, for number 3, it says that 12 cubes are stacked to make a figure. Let's turn my page and we'll take a look at what that figure is. 12 cubes. Here we go. Lovely. What is the surface area of the 12 cubes? Alright, we've done this before, and what I did last time, I just looked at the colors. The colors are very helpful. I have a green, I have blue, and I have yellow. So, the green. I have 1, 2, 3, 4, 5, 6 of those, right? But the 6 that I have here are also on the back side, so I'm going to multiply it by 2 for surface area. So I have 12 green. When it comes to blue, I have 1, 2, 3, 4, 5, 6 on the top, which means on the bottom are 6 more. So 6 times 2 for 12. And the yellow, I have 1, 2, 3, 4, 5, 6 again. But on the back side over here, I have another 6, so times 2 makes 12. So my surface area is going to be 12 plus 12 plus 12, which is 36. Okay, we're good with that one. Now the next question says, how would the surface area change if the top 2 cubes were removed? So if we took these top 2 off, what would we have? Well, we could sketch it out real quick if we wanted to. Okay, we'd have this right here. It's not going to be a great sketch there. And we have 3 going this way. 1, 2, and 3. We know that these ones go this way. 1, oops, that's terrible. That's okay. Okay, there. And then we went up and up and up and yep, and there and there. And if we take those off, then we end up with this. Okay, something along those lines. Not too bad, but not fantastic. So if I chopped off the top, I would end up with the green being here 1, 2, 3, 4, 5. So green is 5 times 2, because the back side, for 10. The yellow would be these front sections here, 1, 2, and then 3 and 4. So yellow is 4 times the back side, which is 2, which is 8. And the blue becomes the top of each of the cubes. So 1, 2, 3, 4, 5, 6. So 6 times the bottom, which is 2, for 12. So in total, 10 plus 8 plus 12 is going to equal 30. So in terms of the surface area, what's happening by taking off just those top cubes is I lose 6 less, right? I went from 36 to 30, so it's 6 less than what I had before. Which, if you think about it, you could have just taken this and said, well, how much space is that showing? These top ones are still going to stick around, right? Because they become the top of the other ones. So what I lose is 1, 2, and the back side, 3, 4, and the green here for 5, and the back side for 6. So we lose 6 by taking out those 2 cubes. Alright, number 4. Here are 2 polyhedra and their nets. Label all edges and the nets with the correct lengths. So we're going to label all the edges. So we have a base of 5 and 4, and this long length of 10. So I know that all these lengths are 10, 10, 10, and 10. Not too bad. I also have excuse me, a length of 5 and 4. So this becomes my 5, which makes this my 4 because they're a little bit shorter there, which makes this a 5 as well. Makes this a 5, this a 5, a 4, and a 4. Now what to do with the next ones? Well, they're going to alternate 5, 4, 5, 4 along the edge of the 10. So that's a 5, that becomes a 4, and that's a 5. That's a 5, that becomes a 4, 5, 4, 4, 5, like so. Alright, just that alternating pattern there. On this next one, we have a 10 and a 4, and these long lengths of 13. So these become my 10s. These short ones become my 4. And all the rest, because the pyramid, are going to be 13 all the way around. We're not worried about the size of those triangles. We're just talking about the lengths, and every length in the pyramid, like that, to the vertex is the same length. It's going to be 13. Alright. The next question says, what three-dimensional figure can be assembled from the net? So looking at this net right here, what shape, three-dimensional shape, can we make with that net? We have a square base and we have 4 triangles. So we would call that a square pyramid. And that's what we would call that one there, because those would fold up. What is the surface area of that square pyramid? Well, let's take a look. We have 1, 2, 3, 4, 1, 2, 3, 4. So then for the square part, it's a 4 times 4, which is 16. And then for the triangle, we have a base of 4, and we have a height of 1, 2, 3, 4, 5. So 1/2 times the base times the height. 4 times 5 is 20, half of that is 10, but I have 1, 2, 3, 4 of them. So I have a total of 40, but let's combine them together for the whole area. We have 40 plus 16 is 56, and these are what? Square units? Square units. And that's it for today. Hope you have a great one, and we will see you next time.